Today's deep generative models often appear as impenetrable black boxes of linear algebra, systems that scale infinitely as long as we keep feeding them data and raw processing power. In reality, architectural evolution in neural networks is driven by a brutal pressure to balance representation power against computational survival. Mathematically, adding nodes in hidden layers guarantees a more accurate representation of data. However, it also causes the time required to calculate gradients to grow exponentially. This graph plots the trade-off. The x-axis measures computation complexity, the energy to train. The y-axis measures representation power, the capacity to learn patterns. Historical progression traces a path upward, from the Hopfield network to the Boltzmann machine, the restricted Boltzmann machine, and deep Boltzmann machine. Moving up this curve required more than larger machines. The breakthroughs occurred when researchers figured out exactly which mathematical connections had to be severed to make the training physically possible. To understand why those connections were severed, we have to look outside of computer science entirely. We have to look to 19th century thermodynamics, and specifically the work of Ludwig Boltzmann. When early theorists attempted to figure out how a machine could memorize data, they looked to how physical systems settle into stable states. They borrowed the concept of energy minimization, the physical rule that a system naturally shifts its internal variables until it reaches its lowest possible energy state. The entire generative branch of artificial intelligence emerged from an attempt to build a silicon network that replicates this precise physical behavior. They wanted a network that cools, settles, and stabilizes exactly like a cluster of molecules. In physics, a phenomenon called a spin glass occurs when magnetic dipoles in a confined space are forced to align with their immediate neighbors. As one dipole flips, it alters the surrounding magnetic field. That causes adjacent dipoles to flip, which alters the field again. This cascade continues until the entire system locks into a stable configuration of minimum potential energy. In 1982, John Hopfield built the computational translation of a spin glass, the Hopfield network. It is a fully connected web of binary thresholding nodes, linked in both directions. By assigning an energy equation to the structure, the network automatically adjusts its states, rolling down an energy gradient and altering weights until it locks into a stable data pattern. The math here is strictly deterministic. The network always rolls directly downhill. Because of this, it rarely finds the global optimum. Instead, it gets trapped in local minima. This rigidity dictates a severe limitation on capacity. An n-unit Hopfield network can only store a tiny fraction of information. If the system attempts to store one more pattern, the memories overlap and corrupt each other. Treating memory as a purely deterministic descent creates a brittle architecture that collapses under the weight of its own data limits. To escape those local traps and increase memory capacity, the math required two specific structural upgrades: hidden units and stochasticity. First, theorists added a layer of hidden units. These nodes don't receive outside data, but assist the visible units in modeling complex, latent variables. Second, they injected stochasticity. States now flip based on a probability distribution derived from thermodynamic temperature, allowing the network to temporarily move up the gradient and bump out of local traps. This structure is known as the Boltzmann machine. The injection of random thermal noise successfully solved the prior capacity constraints. However, it also triggered a mathematical catastrophe during the training phase. The goal of training a Boltzmann machine is to find the parameters that maximize the log likelihood of the observed data. To compute this gradient, the system must calculate the expected joint distribution over all possible combinations of variable states across the entire network. Because calculating every possible state directly is impossible, engineers rely on a statistical sampling method called Markov chain Monte Carlo, or MCMC, to approximate the massive sum. Here is where the architecture fails. Because every node is intimately connected to every other node in a massive web, MCMC sampling must run sequentially until the entire system reaches thermal equilibrium. In physical reality, for any realistically sized model, simulating this many connected variables until they reach equilibrium takes an eternity. Theoretical representation power is useless if the underlying probability gradients take longer than the lifespan of the universe to compute. By 1986, cognitive scientist Paul Smolenski recognized that the MCMC bottleneck couldn't be brute forced with more computational power. Instead, the physical topology of the network itself had to be fundamentally modified. His solution was a precise restriction. He completely removed all connections between visible units and all connections between hidden units. Without those lateral connections, the energy function drastically simplifies as the intra-layer terms drop out of the equation. This creates a crucial mathematical property. The hidden units are now conditionally independent given the visible units. Because the nodes no longer continuously affect their neighbors, the network completely bypasses the need for infinite MCMC sampling. In 2002, Geoffrey Hinton capitalized on this restricted structure with an algorithm called contrastive divergence. His method exploited the bipartite graph to accurately approximate the model distribution in just a single step. Generative AI advanced not through increased connectivity, but through systematic blinding, severing specific links to ensure the underlying math could actually be computed. Once the single-layer restricted Boltzmann machine was mathematically solvable, it ceased to be a complete end-to-end model and became a foundational building block. Researchers began stacking multiple bipartite RBM graphs on top of one another to construct deep architectures. To make this work, they utilized layer-wise unsupervised pre-training. Each stacked RBM is trained one by one, from the bottom up. This initializes the parameters into a stable mathematical space before the entire network is fine-tuned. By allowing bidirectional connections in the bottom layers, the architecture evolves from a deep belief network into a deep Boltzmann machine, increasing its ability to model complex data distributions. The ability to stack these restricted graphs without triggering a computational explosion provided the structural foundation for the models that dominate current research. This chart shows the exact trajectory of that architectural evolution. It starts with the physical alignment of magnetic dipoles in the Hopfield network, moves to the injection of stochastic heat in the Boltzmann machine, and relies entirely on the critical severing of connections in the restricted Boltzmann machine. Deep belief networks and deep Boltzmann machines represent the forced mathematical endpoints of simulating thermodynamics in silicon. The history of deep learning reveals a strict law of design. True architectural breakthroughs rarely come from adding raw computational power. They come from discovering exactly which parts of a network you must destroy in order for it to learn.